welcome to this explainer. Whenever we crack open a modern textbook on thermodynamics, we're instantly hit with all this abstract calculus, pristine state functions, and elegant laws of energy conservation. But to really grasp these concepts, we have to recognize that they didn't start out in some pristine, quiet laboratory. No, they started with a very dirty, very loud, and incredibly practical problem, building a better steam engine. So today, we're going to explore exactly how the grit and grime of the Industrial Revolution actually forged the foundational math of thermodynamics. Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at the steam engine problem. Then we'll ask, what exactly is heat? Move on to Carnot and the cycle. Follow up with the first law unveiled, and wrap up with specific heats of gases. Section 1, the steam engine problem, a practical need. Let me pose a really simple question to you. What actually happens when you rub your hands together? You feel warmth, right? It's so incredibly basic, and yet for centuries, this completely baffled the smartest early natural philosophers. They were desperately trying to figure out the exact relationship between physical friction, mechanical work, and the resulting heat. It was this massive conceptual mystery, and it became absolutely critical to solve as the world started to industrialize. Picture this. It's the turn of the 18th century in Britain, and they have a massive problem on their hands. Forests near population centers were totally exhausted, so they had to turn to coal. But the coal mines just kept flooding. They desperately needed a mechanical solution. In 1698, Thomas Savery introduces this highly inefficient atmospheric boiler to pump out the water. Fast forward to 1712, and Thomas Newcomen improves on it with a cyclic rocking piston engine. But the ultimate game changer, that happens in 1765. A mechanic named James Watt is repairing a Newcomen engine and realizes it's just wasting incredible amounts of heat, so he adds a separate cold reservoir, a condenser. And wow, this completely revolutionized the efficiency of the machine. But here's the crazy part you have to realize. These brilliant engineers were essentially just guessing. They were systematically optimizing these massive, powerful engines through sheer trial and error. They didn't have any unified scientific theory of heat to guide them at all. So they were essentially creating this massive, real-world industrial puzzle that desperate physicists and academics would eventually have to solve. Section 2. What exactly is heat? The great debate. For decades, the scientific community was totally split on this. On one side, championed by Antoine Lavoisier in the late 18th century, you had the caloric theory. This idea argued that heat was actually a weightless, conserved fluid called caloric that literally flowed from hot objects into cold ones. And honestly, it made total sense at the time, especially for early calorimetry, where measuring melted ice felt exactly like measuring a transferred physical fluid. On the flip side, though, was the vis viva theory, an older idea suggesting that heat was actually just the microscopic, invisible motion of particles. Well, that debate was finally shattered in the 1840s, heavily driven by the work of James Joule. Through his famous paddle wheel experiments, Joule definitively proved that you could physically churn water to heat it up. Mechanical work was directly producing heat. They weren't two distinct things anymore. They were interchangeable forms of the exact same thing. The mechanical equivalent of heat was established, the caloric theory was completely destroyed, and this beautiful, unifying concept called energy finally took center stage. Section 3. Carnot and the cycle. Theoretical abstraction. Let's step back slightly to 1824. A young French engineer named Sadi Carnot publishes a profound breakthrough. He wanted to find the absolute maximum theoretical efficiency of a steam engine, so he conceptually strips away all the messy, clunky, real-world parts of Watt's engines and abstracts them into a perfect theoretical cycle of expansions and compressions. He proposes a reversible heat engine operating perfectly between a hot thermal reservoir and a cold thermal reservoir, completely avoiding any direct thermal mismatch. Now, what's really fascinating here is how Carnot's cycle lays the groundwork for thermodynamics in geometric terms. Think about a multipath process on a pressure-volume diagram. When a closed system undergoes a change of state and then returns perfectly to its origin, we have a complete cycle. The algebraic sum of the heat transfers across that entire cycle must exactly equal the algebraic sum of the work transfers. Basically, the cyclic integral of heat equals the cyclic integral of work. This visual logic became the absolute bedrock for what was coming next. Section 4. The first law unveiled. Mathematical formulas. So we are now pivoting from historical problem solving directly into the modern mathematical formulas we use today. With heat and work now fully recognized as interchangeable forms of energy, physicists like Rudolf Clausius realized something profound in 1850. If you take a system from state 1 to state 2, the difference between the heat added and the work done is a constant, regardless of the path you take to get there. This realization gave birth to a brand new state function, internal energy, represented by the letter U. It depends only on the system's current state, and it perfectly tied the messy history of heat and work together. Let's walk carefully through the exact logic of the first law equation. It is incredibly straightforward when you break it down like this. Step 1. You add heat to your system, which we call Q. Step 2. That system does mechanical work on its surroundings, like expanding a piston, which we call W. Step 3. Since energy cannot be created or destroyed, the difference between the heat you put in and the work you got out must exactly equal the change in the system's internal energy, or delta U. And this brilliantly illustrates exactly how the math comes together. Formalized by pioneers like Clausius and William Thomson, you see the integral mathematically resolving into Q minus W equals delta U. Or, for an infinitely small change, it's dQ minus dW equal du. This right here is the non-flow energy equation applied to any closed system. It's the first law of thermodynamics, the ultimate law of energy conservation. Section 5. Specific heats of gases, applying the first law. Now, different gases absorb heat completely differently depending on their physical conditions. If you hold a gas at a constant volume, we use the specific heat capacity CV. But if you hold it at a constant pressure, allowing it to expand, we use CP. Because holding the pressure constant actually allows the volume to change from V1 to V2, work is actively being done by the gas. But if you hold the volume constant, the gas simply cannot expand, meaning it literally cannot push against anything to do work. Let's break down the exact math of that constant volume condition, which is known as an isochoric process. Imagine your gas is trapped in a completely closed, rigid, unyielding metal vessel. You heat it up. Because the walls literally won't move, there's absolutely zero change in volume. Therefore, work, or W, is exactly zero. Following our first law equation, if W is zero, then all the heat Q that you are supplying goes directly and entirely into raising that internal energy. Q equals delta U. Let's see how this builds visually on a pressure-volume diagram. Think about a straight vertical line moving from state 1 to state 2. The volume is completely constant on the x-axis, right? Since mechanical work mathematically is the integral of pressure with respect to volume, which is just the area under the curve, a straight vertical line has absolutely zero area under it. This elegantly proves visually exactly what we just proved mathematically. Zero area under the curve means strictly zero work is done by the system. And this leads us straight into the fundamental relationship between those two specific heats. Because heating a gas at a constant pressure requires extra energy to do the actual work of expansion, Cp is always going to be greater than Cv. By using the property of enthalpy, H, and the ideal gas constant, R, the math shakes out perfectly so that Cp equals Cv plus R. These algebraic derivations tie right back down to the fundamental physical properties of the working fluid that those early engineers were sweating over a century prior. Which brings us to our final takeaway. The first law firmly established that a perpetual motion machine of the first kind, a machine that just conjures up mechanical work from nowhere without consuming energy, is fictitious. It is absolutely impossible. Because of the relentless, inescapable math forged by those early engine builders who were just desperate to drain coal mines, we now know the definitive truth of our universe. You can never, ever get something for nothing. So it makes you wonder, what kind of modern technologies are we trying to build today where we're still fighting against that exact same immovable boundary? Keep learning, and I'll see you in the next explainer.